Hello, hello. Okay, so today we are going to be doing applied probability again. These are not my slides, so let's get right into it. The topic we're discussing is this derived distribution for function of two random variables. I don't want this to be here or be here. Yeah, it's like that. Discrete case for discrete random variables. We deal with probability mass functions. The probability mass function tells you the exact probability of the variable equaling a specific number. Finding the derived probability mass function. To find the probability that z equals a specific value, you must find every possible combination of x and y that makes the function equal z. Then you simply add up the joint probabilities of all those specific x, y pairs. I think, yeah, this is much similar to what we've done previously. Finding the derived CDF cumulative distribution function. The cumulative distribution function measures the probability that z is less than or equal to a value z. Okay, as we stated, up till the value z. The logic is exactly the same as the probability mass function, but instead of looking for exact matches, you sum the probabilities of all x, y pairs that result in a value less than or equal to z. To the continuous case. Okay, we're moving on to continuous. That was discrete. For continuous random variables, we deal with the probability density functions. You cannot calculate the probability of a continuous variable being an exact value. The probability of an exact value is almost zero. Instead, you must calculate probabilities over ranges or areas. Because of this, finding the PDF directly is mathematically difficult. Therefore, we use the standard two-step procedure as we've learned before. Oh wait, I don't think I've learned it on the stream. Well, anyways. Compute the CDF of z, and then we have to obviously differentiate. First, find the cumulative probability. And you do this by setting up a double integral of the joint PDF. f of x, f of xy bracket xy over the region in the xy plane where the function g of xy is less than or equal to z. Okay, now that's the equation, double integral. Step number 2. Okay, step number 2. Once you have the mathematical expression for the CDF f z, you can use the fundamental theorem of calculus. The derivative of the CDF gives you the PDF. Yes, it does. Now, I think only our concise exam notes are left. Let's quickly go through these. Given joint distribution of x, y, find the distribution of z. Discrete random variables derive PMF sum, the joint probability of all x and y pairs that evaluate exactly to z, as we've done before. Derive CDF sum, the joint probabilities of all x y pairs that evaluate to less than equal to z. Yes, as we know how CDF works. Continuous variables, we just changed that up to a double integral on the. Oh no, we actually use the two-step method. Find the derived CDF via double integration. We find that area under the curves, double both axes. Find the derived PDF via differentiation. Take the derivative of the CDF you found in step 1 with respect to z. Yeah, understood. Let's get the new slides in now. We have an example on hands now. Quite similar to what we did in lecture 11, but again, you don't know what that is, so I'm sorry, I didn't couldn't do it. I couldn't like put that in the stream, but I'll probably have a lecture of that. See, when am I get the time for that? I don't know. Maybe no, can't do Tuesday. Can't do Tuesday. But I think I will have time to do that. Should we do two examples? God, there's 3 examples. At least 3 that I can see. Let's do 2 examples right now. Let's knock them down quick. These examples apply the 2-step procedure. Find the CDF, then differentiate to find the PDF. 4. Continuous random variables. Because x and y are both independent and uniformly distributed on the joint PDF is simply M11. Okay. Example number 1. Since x and y are between 0 and 1, their sum z must be between 0 and 2. We are looking for the probability x plus y less than or equal to z, which corresponds to the area under the line x plus y is equal to z, or y is equal to z minus x. Because the shape of the area changes as the line moves across the square, we split it into 2 cases. Case 1, 0 less than or equal to z less than or equal to 1. The line cuts across the bottom left corner, forming a small shaded triangle. CDF the area. The triangle has a base of z and a height of z, so z squared. Next we have the PDF. For the PDF derivative, we have, well, we just take the derivative. We get z for that. Wait, how do we get z? Wait, let me just think about it. We shouldn't get z, right? Should we? Z22. Oh, yeah, we do get z. Sorry about that. Okay, case number 2. 1 is less than or equal to 2. Okay. Why do we have two cases, though? We'll search that. Visual, the line has moved past the center. The shaded area is now a complex polygon. It is mathematically easier to calculate the area of the square, which is 1, and subtract the unshaded top triangle. CDF area. The unshaded triangle has a base area of 2 minus z. Let me think how we got that. I don't know. 2 minus z. How the hell did we get 2 minus z? I saw your face today, not tomorrow. It's the tree. Shaded triangle area. How is it 2 minus z? I'm gonna have to search that. How do we have two cases and how is... Okay, so apparently 2 is like this upmost area because 1 plus 1 is equal to 2 somehow. Okay, that's what like it's telling me. Why do we have two cases? The line sweeps through the square, but the shape of the area under the line changes depending on whether z is less than 1 or greater than 1. When z is a small fraction lying z equals 0.5, the line x plus y only cuts across the bottom left corner. What the hell is z? I don't understand it. We're talking about area. Z could be the area. Okay. No, it's not the area. Okay. Hmm. So z minus 2 area of the unshaded triangle. 1 over 2 into base into height. Base into height would logically be the same, so assuming 2 is the highest probability, so you have to plus 1 plus 1. Still don't understand that. Still don't understand that. Let's see what z square far up down. I don't understand this shit. If that's z, there's a lot of notifications coming out of my phone right now. Yeah, you know where you are. You know where you are. Maybe this salt near provides some much needed clarity. If I is clarity on is clarity on you, clarity on clarity on Okay, now example 2. Ratio of two uniform variables. Okay, here z represents the ratio. So z can change from 0 to infinity. We want the probability that x or 0 is less than or equal to z, which rearranges to blah blah blah. This represents the area under a line passing through the origin with a slope of z. Yes, it does. Again, the geometry dictates two cases based on where the line intersects the edges of the unit square. 0, 1, shallow slope. The slope is less than 1, so the line cuts its right side of the square at x is equal to 1 and y is equal to z. The shaded region under the line is a triangle. CDF area. The area has a base of 1 and a height of z. PDF derivative, case 2. Let's put that into here. So up until here it's case 1, then here it's case 2. Got it, simple enough. Until it's not, you know. Hopefully it still remains that way. Which will. So derivative, we found the PMF. Sorry, we found the CDF. We derivate that to find the PDF, and then we have case 2. Case 2 greater than 1 steep slope. Visual, the slope is greater than 1, so the line exits at the top of the square at y is equal to 1, and x is equal to 1 over z. Why is x equal to 1 over z? Interesting. Why the frick is x equal to 1 over z? The shaded region is a trapezoid. Like example 1, it is easier to subtract the unshaded top left triangle from the total area of 1. CDF area, the unshaded triangle has a height of 1 along the x-axis and a base of 1 over z along the top edge. Derivative, we derive that and we get this, blah, blah, blah. How do we get z to that? That's something I want to understand. Holy shit, like just give me a minute, there's crumbs all over my table. There's crumbs everywhere. Let there be no dance. Let there be no dance. All right. How to get 1 over z? That's the thing. That's the thing. How the frickle dickle did you get 1 over z? The slope is z. How to get 1 over z? Let me search that up. Let's also put cheat sheet here. We'll go over this soon. Steep slope, because z is less than 1, the slope of the line is steep. An angle of 45 degrees. The higher because it is so steep, line shoots up and it's the top edge of the one plus square before you can reach the right edge. Yes, find the intersection. We need to find the exact coordinates of where the line posts through the top of the square. We know the entire edge of this square is fixed at a height of y is equal to 1. We know the equation as y is equal to zx. To find where the meet, we substitute 1 in for x, and we just solve both sides. Okay. let's do this and let's quickly move on forth. There's an example 3, there's an example 4. There is an example 5. Oh my god. Oh my god. Oh my god. They're just examples and like examples. Anyways, what does it say? If x and y are independent and uniformly distributed all on 1 1, I think it's writing dollar sign because it doesn't know how to deal with it. It actually should be 1 1. Their joint PDF is f of x y bracket x y 1. Therefore solving the double integral for the CDF is identical to finding the geometric area of the valid region inside the 1 by 1 square. Define the region. Write the inequality. Sketch the 1 by 1 square. Draw the line inside the square. Identify boundary cases. Determine at what values of z the shape of the area changes. Calculate area. If the region is a simple triangle, use 1 over 2 bh, base area into height. If the region is a complex polygon, use 1 minus area of unshaded triangle. Take differentiation of your area equations to find the precise piecewise PWF probability density function. Okay. Let's move on. I think I could like probably put all of the examples together. Because I'm too goddamn lazy. Let's go. Let me just do this for that. So it makes it easier and quicker. We have Romeo and Juliet again. Okay. Hello, where you are, babe. Hello, where you are. So again, these are not my slides. I'm just learning from them and probably helping you learn. Did not mean to do that. Hold on. Oh, okay. Example number 3, difference of two uniforms. There we go. This is very similar example to example 1, but we are subtracting. X and y are still trapped in the 1 by 1 square. The setup, if x can be anywhere from 0 to 1, the y can be anywhere from 0 to 1. What is the possible range of their differences? Maximum is the largest possible 1, and y is as small as possible 0. Minimum -1, so it ranges from -1 to 1, yeah. So the geometric trick. Each of these examples includes a trick, which makes us solving calculus for us a lot easier. We're looking for p x minus y is equal to z, which ranges to blah 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 on a graph. Y is equal to x minus z is a straight line with a slope of 1 shifting up and down depending on z. Okay. Slope of 1 shifting up and down depending on z. Because we want y is greater than or equal to x minus z, we are looking at the area above this line inside the 1 by 1 square. Case 1. -1 is less than or equal to z is less than or equal to 0. Z is negative, so the line is shifted up. The area above the line is simple triangle in the top left corner. Top left corner. So we just find the area, which is the CDF and PDF. Differentiate that CDF. Case number 2, 0 to z is equal to 1. Z is positive, so the line is shifted down. The area above the line is a 5-sided polygon like before. Why is the area above? Okay, whatever. Becomes 5-sided like before. We take the total area 1 and subtract the small unshaded triangle in the bottom right corner. So what's happening is, I think we need a little visual. So what's happening is, we have a line and we have a line. Okay, then we can call this x, we can call it y, we can call this x. And we have a square right here. And it's square like that. And we have in the bottom, what was it? Let's change something. So this is our line, okay? This is our line, which is equal to z. Now z can either be here or it can be here. So this is case number, this is case number 2. All right, I think we understood that. Let's move on. Example 4.9 are Romeo and Juliet. Here x and y represent the time Romeo and Juliet arrive. We did this type of example before. They are exponentially distributed, meaning they can arrive anytime from 0 to infinity. Because there is no one square boundary, we cannot use geometry. We have to use double integrals. That's sad because As we stated, there's no boundary. Set up a double integral from 0 to infinity as tedious. This slide uses a brilliant logical shortcut, symmetry. Because Romeo and Juliet have the exact same arrival habit, same exponential parameter, the probability that Romeo is 5 minutes later than Juliet is identical to the probability that Juliet is 5 minutes later than Romeo. Mathematically, this means the distribution of z is equal to x minus y is perfectly mirrored across 0. What do you mean it's mirrored across 0? That's the thing I don't understand. Mirrored across 0. Because the diagrams, they don't show it as mirrored across 0. Anyways, let's move on forth. Let's actually ask that. Okay. Here's what it is telling me. I make that too large. That's good enough. The diagram in the slide where figure 4.6 is graphing the inputs, where it says Julia's around the office of the total. It shows the physical area we need to integrate of. Find the area of the figures. Left side greater than 0. Imagine 0 is equal to 5. We want to find the area where Romeo arrives more than 5 minutes after Juliet. This is a small wedge strictly in the bottom right corner. Right side, imagine z is equal to minus 5. We find the area where Romeo's time minus Juliet time is greater than minus 5. This area covers almost the entire graph because it includes all scenarios except the extreme ones where Juliet is massively late. So we're just asking two completely different questions. Okay. God, this is very confusing. So if these shapes change depending on if z is positive or negative. They look asymmetric. The symmetry refers to the final calculated probability of the new variable z. If you graph the final probability of z, you will get a perfectly mirrored two-sided bell curve. All right. Intriguing. Hold on. Let me integrate both sides. This is the integration of that one. So we will write it as the entirety of this. When you differentiate both sides, you get a beautiful mirrored PDF called the Laplace distribution. Two archers shoot. Solution. Okay, solution is continued here. That's a pretty long continuation. I mean, like, I guess we don't need it, but anyways, 4.7, the archers. Two archers shoot. X is the distance of the first shot from the center. Y is the distance of the second shot. Z is the distance of the losing shot. The losing shot is whichever one is further away from the center. Therefore, Z is equal to max X, Y. The maximum trick. This looks incredibly hard to graph or integrate, but there's a pure logic trick here. We want to find the CDF, the cumulative distribution function. Pz is less than or equal to z. Substitute our function, which is max xy. Ask yourself, if the maximum of two numbers is less than z, what must be true about the individual numbers? They both must be less than z. Yes, that's true. That's true. I think I want to move this to here, move all of this here. Yeah, that's good. That's good. Right. Good. If I were to tell you the tallest person in the room is under 6 feet tall, that guarantees that every single person in the room is under 6 feet tall. Yep. Therefore, we can write the probability P max xy is less than or equal to z is equal to p of x is less than or equal to z, and p of y is less than or equal to z, or y is less than or equal to z, or just x is less than or equal to z. Because the archers shot are independent of each other, we can split the and into multiplication. Since x and y are both uniform on 1 and 1, their individual CDFs are just z. So the combined CDF will be z squared. To find the PDF of z squared, we integrate, we get to z. Pretty damn easy, pretty damn easy. Of course, there's like a lot of mental gymnastics to get up to that point, but overall, I would say that it's pretty straightforward as compared to the other questions that we've done, especially of other topics. I know where you are. I know where you are. Okay, let's move on. Let's add more slides. How many more examples are there? Oh my god! You know, let's add in an example as well, because why not? We have to go through them eventually, so let's go through them now. You have convolution in this. These slides introduce a completely new direct method of finding the distribution of z is equal to x plus 1. It's called convolution. Of course it is. Previously, in example 1, we used the two-step procedure where we found the geometric area for the CDF and then took the derivative to get the PDF. That method always works, but it can be tedious if your two variables are independent and you are specifically adding them together. Z is equal to x plus z. You can skip the CDF entirely and use the convolution formulas to find the PDF or PMF directly. Okay. The discrete case. Imagine rolling two dice, or die. Isn't the plural of dice die? Anyways, imagine rolling two dice, x and y. You want the total sum z to be exactly 7. Z is equal to 7. If I tell you the first die rolled 3, what must the second die be? It must be 7 minus 3. Over here it uses die. 7 minus 3 is equal to 4, so y must be exactly z minus x. To find the total probability of getting a 7, you just list out all the possible rules for x, figure out the required rule for y, and add up those probabilities. This is exactly what this formula says here. All possible rules for x, figure out the required value for y, and add up those probabilities. Yeah, that makes sense, okay. The continuous case. The continuous case is the exact same logic, but because we are dealing with continuous ranges, two, three, four, five, five. The continuous case is the exact same logic, but because we are dealing with continuous ranges, instead of distinct numbers, the summation sign turns into an integral. Okay, the integral essentially takes the PDF of x, takes a flipped version of the PDF of y. Okay, flipped version of the PDF of y slides them across each other, measures how much they overlap at any given point z. Okay, that's basically what convolution is. The example, let's actually bring this over here. Why not? This is the exact same problem as example 1. X and y are uniform over 0 and 1. And it's solved using the convolution integral instead of 2D geometry. When you convolve two identical rectangular uniform distributions, the result is always a triangular distribution. As the rectangles overlap 0 less than equal to z less than equal to 1, the area of the overlap grows linearly, giving you the upward slope z. It doesn't understand, but I'll just take your word for it. As the rectangles slide past each other, the area of the overlap shrinks linearly, giving you the downward slope 2 minus z. From what I understood, this is what's happening in convolution. I mean, again, we should have learned this in signals, but we didn't. Because, well, that's just another thing entirely. What's happening is we have let's call a line. On this, we will have two rectangles. Okay, let's call them A. Let's call this B. They're moving towards each other. Then, afterwards, this, what we get. God damn it. Forget. Afterwards, this, the next thing that we get is well, overlap between these two. Overlap between these two. I made a square. I did not mean to make a square. Here you go. Overlap between these two. Now, the area of the overlap that is what the convolution is showing. Well, shows, which is, you know, which was, a triangle. So over here, this could be this, and then this would be when the rectangles, they sort of overlap the most. For instance, why can't I do that? This is when they overlap the most. And over here is when, they start to move apart again. God, I just wasted a lot of time on that. I did not need to do that. But hey, and that's literally it. Oh my God. Let's give our concise notes. Put in our concise notes here. Let's quickly read through these. Convolution meant use it. You are finding the distribution of z is equal to x plus y, and x and y are independent. Independent, what does that mean? Well, independent is that they are not in any way, shape, or form related to each other. The probability of one happening does not affect the probability of the other happening. Discrete. This is the discrete formula. That's the continuous formula. Key properties and shortcuts to memorize. Uniform plus uniform is equal to triangle. The sum of two independent, identical uniform random variables which correlate to rectangles as we stated results in a triangular distribution as we just stated. The order doesn't matter. X, y is the same as y, x. You can swap which variable gets that z minus x inside the formula. Pick whichever one makes the math easier. Obviously. Limits of integration. Even though the formula says minus infinity and infinity, the actual integral balance will be determined by where the functions overlap. For uniform variable, you must split the integral at z is equal to minus 1, z is equal to 1. You must split the integral at, just like we split the geometry in example 1. I do not understand that, but okay. Oh yeah, I understand that. Okay. We'll understand more because now we're gonna do the examples. More examples actually. Example 4.11. Why is there sigma or standard? Sigma was standard deviation, am I right? I think so. God damn it, we got that shit here again. I just want to teach something easy for once. You want to learn something easy for once, but no. God, no. Stuck in this hellhole. Literal goddamn hellhole. Sorry. 6 minutes, we have to finish this quick. Example 4.1, sum of two normal variables. In this example, ask what happens when you add two independent normal bell curve variables together. So we plug the horrifying formulas for the normal PDFs into the continuous convolution integrals. What are the formulas? These formulas? And we integrate that, okay. No, we multiply them. Okay, the slide explicitly states the details are tedious and omitted. If your professor skips the algebra, you definitely don't need it to do in the exam, but the result of that massive integral is one of the most beautiful and fundamental rule in all of statistics. When you add two independent normal variables together, the result is always, apologies, the result is always another normal variable. New mean is just the sum of the old means. The new variance is the sum of the old variance. Okay, you got this equation. Now we got our next example. Again, Romeo and Juliet. This is the exact same problem as 4.9. Romeo and Juliet arrive at exponentially distributed time. What is the PDF of the difference? Z is equal to is equal to x minus y. But this time we are strictly using the convolution formula instead of the 2D area method. The subtraction trick. The convolution formula: f of z is equal to f of z is equal to f integration f of z is equal to integral f of x, f of y. The overall convolution formula is explicitly designed for adding the variables x plus y. How do we use it for subtraction? We simply rewrite z is equal to x minus y as an additional problem. To do this, we need the PDF of minus y if y is a positive arrival term. Y is just the negative version of this. Easy enough, just put a negative on it. Plug this into the convolution formula. The minus y flips the sign inside the function. Yeah, okay, this flips the sign. Okay. The integration limits trick. This is where most students get stuck. Why did the integral bounds change from minus infinity to z on the slide? It has to do with the rules of the exponential distribution. Exponential variables cannot do negative, so the PDF is only non-zero when the input is greater than or equal to 0. What? I don't understand this. Exponential variables can also the series. For f of x to be valid, we need x is greater than 0, so it can't be negative, okay? For x minus z to be valid, we need the inside to be positive, which means x is greater than z, okay? X is greater than z, so our lower bound will be z. If we assume z is a positive number, then x must be greater than z for both functions to exist at the same time. Therefore, our integral starts at z goes to infinity. When you evaluate that integral, you get the exact same right-sided answer as before. This isn't like exam cheat sheet. Finishing this off. For the left side, z is less than or equal to 0. The slide completely reuses the exact same symmetry trick we learned in example 4.9. So you get the mirrored half of the Laplace distribution. I do not understand what the hell that means. It's probably this slide also for the case. Z minus 0 is obtained with a similar calculation or alternative or alternatively by noting that f of x minus y is equal to z is equal to f of x minus f of y minus x is equal to f of y minus x z is equal to whatever this notation is. I'm not going to say it all. What it does is, as we stated, using the same mirrored half trick of Laplace distribution, which we studied in example 4.9, where the first equality holds by symmetry since x and y are identically distributed. z is less than 0. Before that, we did z is greater than equal to 0. That's what we did. Okay. Let me just look at example 4.9 again. 4.7, this is 4.9. This type of thing, which is less than equal to 0. In which we did all this, say. God, this really melts my mind. I still don't think I understand all of this. I need to go over all of this again to just get a fraction of the idea of what this I learned. God. Let's just read the exam sheet and be done with this. I don't think I need an overall overview of this all. Just have a understanding of what the hell just happened. I didn't understand much. Let me be honest with you. And I have a quiz on this. God damn it. The normal addition will memorize this. If x and y are independent normal random variables, their sum z is equal to x plus y is always normal. New mean. Yeah, in the variance short quiz, you almost never have to do the convolution integral for normal distributions. On exam, just use this property. Yes, I will. Yes, I will. But we have to find, the independent normal variables, their sum. How do we find that? I don't remember. Or will it even ask us to find that? Well, we'll see. The convolution subtraction trick. If a problem asks for z is equal to x minus y using convolution, treat it as what is the time? Don't tell me it's 2 o'clock. God damn it, it's almost 2 o'clock. If a problem asks for z is equal to x minus y using convolution, treat it as z is equal to x plus bracket minus y. Modify the standard equation. Instead of f of y z minus x, it becomes f of y x minus z. Formula f of z is equal to integral minus infinity to positive infinity f of x f of y x minus z d of x. Watch your bounds, exponential random variables. When convolving random variables that cannot be negative like exponentials, the bounds of your integral from minus infinity to positive infinity will shrink. Always set the inside of the PDF is greater than or equal to 0 to 5. Always set the inside of a PDF probability density function. Interesting. To greater than 0 to find your starting bounds. If you have, then x minus z is equal to this, so your integral starts at z. This is just for our specific, what you might call it, example. But always set the inside of the probability density function is greater than 0. So we assume that x minus z is greater than 0. For that to happen, x has to be greater than z. Okay. God damn it, that's all. That's all.